who will tell us about GMN construction of hyperkahler metrics on focus-locus fibration.
Okay. So first, I want to say thanks to the organizers to give me the opportunity to share my study of GMN construction. And also, I want to say thanks to Andy for helpful discussion. Okay. So this talk is mainly based on two papers. One is the original paper given by Gaito, Mori, and Naisky. And another one is the online notes given by Andy. Okay, so first let's do a quick review of the GMN construction. The construction is about some new approach of construction of hyperkahler metric on integral systems, which include the elliptic K3 surface and also Hitchin systems. And in the construction, we need some important data. That's central charge, BPS number, and the wall crossing formulas. Use this data, we can construct the metric by construction of the Hitchin's twisted space. But since the wall crossing phenomenon exists, we need to solve some Riemann-Hilbert type problem. Then we get a metric. Okay. After their paper, there are a lot of great work follow this project. Here I just list some mathematical progress on this construction. The first I know is the work given by Chen Guohui. It's about SYZ mirror symmetry happen on their construction. The next one is given by Lu Wenshen. He proves some equivalence of Kontsevich-Sobolev wall crossing formula and the Gross-Seibert wall crossing formula in their project. And then the next one is given by Cesar. He's doing some systematical research on this Riemann-Hilbert problem. And most recently, there is work given by Yushen Lin. In his thesis, he defined the S1 family version of open Gromov-Witten invariant. That turned out to be a mathematical candidate for the definition of the BBS number and the central charges. And today in our talk, we just focus on another topic. That's a reconstruction problem of Gromov-Witten metric. Ogre-Waffa metric. Since we know Ogre-Waffa metric is an important application of GMN's construction. And we try to address the following two problems. One is the natural way to derive the central charge for the construction of metric. The next one is about some discussion of the uniqueness. Okay. And from my study, somehow it turned out the answer comes from the simplex geometry, especially that's about Lagrange fibration. So first, let's introduce some definition in symplectic geometry. The first one is a focus-focus singularity. That's about singularity happened in four-dimensional Lagrange fibration. The singularity is isolated singularity. And around that singularity, we have a good double chart such that the symplectic form and the fibration have this standard form. And you can see the picture here. It have different names in different language. In singularity theory, we call this is A1 singularity, also called type 1 singularity. Okay. And here's a small trick. In calculation, in practice, generally we will take a complex structure on the total space and on the base to make the expression of symplectic form and the projection simple, like this. And later, when we talk about the norm form and the local models of these, we will use this simple expression. Okay. Then comes focus-focus fibration. Topologically, that's just the partial compactification of the focus-focus singularity. Just imagine somehow you glue the top and end of each cylinder fiber of the focus-focus singularity, you can get the torus fibration. And here we just allow one singularity, one focus-focus singularity happen on the singular central fiber. Okay. And in physics and mathematics, there are a lot of examples of such singularity. The first one is the Ogre-Vafa space. Originally, that's the S1 fiber bundle over R2 cross S1, but you can lift the S1 direction also into the fiber direction. That will give you the torus fibration. And the second one is a famous example in mechanics. That's a spherical pendulum. And the next one is most important example in so far in the study of mirror symmetry. That's a gross example of special Lagrangian fibration. That's a fibration from C2 minus a divisor to C. And the symplectic form is given by some deformation of the standard Fubini-Stony metric. And also, we have a bunch of other examples comes from local elliptic K3. Just imagine you have elliptic K3, you use that hyperkahler rotation, you get a Lagrangian fibration. And since you have singular fiber, singular point is isolated. So that's the only case. OK, now let's talk about the importance of this focus fibration. So here, we need the classification result of such fibration. First, we want to define some equivalent relation between two fibrations. The equivalence is given like this. If you have two focus-focus fibration, and there exists a fiber-wise symplectic morphism, so that's a symplectic morphism of the total space, and also a map from fiber to fiber. In that sense, we call the focus-focus fibration equivalent. Then it turns out such equivalent class can be classified in the following way. You can cook up some local model or normal forms like this, and it contains some classification data. That's local invariant. And we call that semi-global invariant. So first, let me tell you how to cook up the total space, and then tell you what's the meaning of this data. Okay. So the total space comes in this way. Topologically, that's a gluing of focus-focus singularity. So that's the original focus-focus singularity. Then what you do, you take two Poincare surface or two Lagrangian sections. That's a pi1 and pi2, given like this. Pi1 and pi2 are two Lagrangian sections. Then on each fiber, you hit 2 points. Okay. Now you do the gluing. On each fiber, you define the gluing of these 2 points, given by the two sections. Then how about the rest? Notice that in the focus-focus singularity, you have two Hamiltonian actions. One is the dilection in the cylinder direction. Another Hamiltonian is the S1 action. So you use S1 action to move out S1 on one end, and another S1 on another end. Then since the S1 action is globally act on the fiber, so you can define the gluing of S1 and S1. Okay. So in this way, we can glue this total space. For focus-focus singularity, the total space is R2. Now you do such gluing, and we call the space is a model space. Okay. And the symplectic form is still this symplectic form. Of course, you need to check such gluing will keep the symplectic structure. Okay, so that's the first two data. Now let me tell you what's the meaning of this S. First, the S belongs to the space of smooth function on the base. Let's call the base is B. Then S is just a smooth function there. But we have the condition. The value should vanish at the origin, at the locus of the central fiber. Okay, and here we have data S1, S2. That's just a partial derivative. Okay. Here I take a complex coordinate C equal to C1 plus IC2 on the base. So that's a partial derivative. Now, what's the meaning of this S1 and S2? That's about the choice of a second Lagrangian section. As we know, we have two Hamiltonian actions. So you need the data to locate this point. How far should you choose this point? How far you should go follow these two Hamiltonian action? Then the first data give you the time you should follow the first Hamiltonian action. The second data give you the data about the time you should follow the second Hamiltonian action. Okay. So that gives you the location of this choice of second Lagrangian section. Okay. So this is just dynamical meaning of this. Okay, so just remember the model case is some gluing of C2. Omega is the standard one. S is some smooth function. Its partial derivative will give you the dynamical meaning of this Hamiltonian action. Okay, now let's go back to the examples. As I said, we have a lot of examples. First one, the Ogre-Vafa one. By calculation, we can show the semi-global invariant is just 0. That's the best case. And recently, there is a calculation given by Hodge-Dulin. It's about the spherical pendular. It turned out the invariant is like this. Then how about the gross example? So far, it's not calculated yet because the calculation always involves the abelian integral, so not so explicit. And generally, for local elliptic K3, if you imagine elliptic K3 is coming from hyperkahler rotation, then later we can show this invariant must be harmonic. Okay, now let's talk about the idea how to construct the metric. So we follow GMN construction. We take the central charge to be some holomorphic function determined by action coordinate. The BPS number is just +1 and -1 because on the K3 case, locally near the singular fiber, you just have one family of holomorphic disk. Right? And then the semi-flat metric can be written down by action angle coordinate. Then we do the GMN quantum correction. And finally, we apply the removal singularity argument to say this metric extended over a singular fiber. Okay, so first let's write down the action angle coordinate. That always exists on Lagrangian fibration with Lagrangian sections. Right? So by a deuce mat construction, first we take a Lagrangian section. So here we just take a simple one. Then we let the Lagrangian section move with the Hamiltonian flow. Then you can write down the action angle coordinate. That means by some simple coordinate change, you can make the pullback symplectic form to be the standard form. Okay. And as we know, different choice of Lagrangian section will affect on this action angle coordinate. So we have some freedom left here. Okay, now let's see why this construction is related with hyperkahler metric or related with K3 surface. Because locally we know you can imagine somehow focus-locus fibration comes from a total neighborhood of a singular fiber from elliptic K3, right? Now let's borrow some terminology. We call the normal form, which constructed previously, is local K3 if it admits two form with this characteristic property. That's a property for Calabi-Yau. And also the real part is the standard one. Then we can show that a normal form is local K3, as we define here, if and only if the semi-global invariant is harmonic and its lower bound for the partial derivative. Okay. Then under such conditions, in fact, we can write down the holomorphic 2 form. It comes in this form. Here we have a different notation. That's a capital Z. Yeah, here we just use small z, the normal z, but here we use capital Z. Capital Z is the central charge we call it in physics. It's a holomorphic function, and the relation with our action angle coordinate is the real part of the central charge is just the action coordinate. Okay, and notice that here we have some term h left. We don't like this, but you can show if the Lagrange section is also the Lagrange section with respect to the real part of omega is also Lagrangian with respect to the imaginary part of omega, then this term will disappear. That's the case happened if you take holomorphic section on K3, then you do hyperkahler rotation, that goes to the case by Lagrange section, so it will disappear. Okay, then for physically, we can write down the canonical Kahler form like this, and then we can show this is indeed the 1-1 form. Okay, and this condition tell you if that's a metric, the Ricci curvature is 0. Okay, now we can say something like this. The canonical form is in fact Ricci flat or hyperkahler on the regular part with respect to the complex structure determined by omega, if and only if that's a previous condition. And here comes an extra condition. That's about the positive property of the metric. And remember, in the Ogre-Vafa case, we have S equal to 0. So that's automatically true in that case. Okay. And remember here, all the construction so far is only happened on the regular part. So it's away from the singular fiber. And generally, we can show the metric, the canonical metric cannot extend over the singular fiber. Okay. Then comes the amazing idea of GMN's construction, how to do some correction of the canonical metric, make that extendable over the singular fiber. And it turns out the idea is we do not do the correction on the metric directly, but we do the correction on the associated Hitchens twistor space. So what we do? First, we write down the CP1 family of the holomorphic 2 forms, do linear combination like this. Then, by observation, we can write down the holomorphic 2 form in a better expression. That's an expression given by the holomorphic double coordinate. Okay, so it's kind of amazing. If you do some combination like this, you get the expression. Now let's say a little bit why we choose a combination like this. How do we figure out that's a choice?
What is R for you? What is
R is arbitrary real number. Generally that's a size for the S1. Okay, so recall that we have the central charge and the angle coordinate like this. So you can check we have the global monogamy like this. So if you want to combination of a central charge and the angle coordinate and make that compatible and induce some complex structure, that's a unique way you do the combination. Although you have the global monogamy like this exist. Okay. Then turned out the amazing idea, somehow how to do the quantum correction of the metric. It turned out when you can do some correction, cancel such global monodromy of the holomorphic double coordinate, then you can make the metric extendable. Okay. So here comes the main formula of GMN construction. You take the inverse monodromy, you cut the plane into two half, and take the BBS rings. You do the integrals. Then you can construct the inverse monodromy. The inverse monodromy here will cancel the original one. Then finally, you can get some global defined holomorphic two forms. Okay. Then what you do is just do the calculation. Remember, we can return to the metric from the twisted space. Then we can recover the general Ogre-Vafa metric. That's a metric with a potential function equal to the standard one given by Ogre-Vafa and plus a harmonic function here. And so somehow we give a geometrical explanation of this holomorphic term. That's our semi-global invariant. And if you are familiar with Gross and Wilson's construction of approximation of a Ricci-Fleck metric on K3, then you will notice this is their model of metric. Then do some gluing. And here, recall that the Ogre-Vafa potential is given in this way. So phi here is just the fundamental solution on R3, which is singular at the lattice point. Okay. Then you put this function into the Gibson-Hawking ansatz. You get a metric, which is good. There's no singularity happen, so you can extend over the singular fiber. Here the harmonic theory comes because that's the order. You want to make the function converge. Okay, now let's summarize the result today. The result is, first, we get a natural way to derive the central charge to construct the Ogre-Vafa metric. So what we do is study the normal form of focus-focus fibration, and it turned out that the action coordinate is the real part of the central charge we want. Remember, the central charge is holomorphic function, and the action coordinate is harmonic. So in the C1 case, they will determine each other, right, uniquely. And the second one comes from the construction of action coordinate. Remember, we have some freedom left. One freedom is the choice of Lagrange section. If you change the section, you will change the coordinate. And the second freedom left is a semi-global invariant. Right? You can choose that to be 0. That's the original Ogre-Vafa metric. And you can choose that to be other positive harmonic function. Then you can get other expression of a Ricci-Fleck metric. Okay. So third, there are some simple generalization of this result. So far we just talked about the A1 case. Now maybe you ask, what about A2 case or A3 case? The idea is quite simple. For example, if you want to construct some metric on the A2 case, so what you do is you just take 2 copies of the A1 case. But with the same semi-global invariant. Okay. Then remember, what's the focus-focus fibration? That's the one we glue the top and end. So that means if you construct the metric here on focus-focus fibration, that's the metric allows some compatible gluing of top and end, and also for this one. Okay. But since it's a compatible condition, so there's no difference if you glue this top to this end and this top to that end. Then the metric is still compatible for the gluing. And after this gluing, you get the central fiber have 2 A1 singularity. That's equivalent to A2 singularity. So in this way, you can cook up arbitrary metric on arbitrary AK singularity. Okay, so far that's just the local picture. So finally, we want to touch the global metric. That's a Calabi-Yau metric on elliptic K3. But that's kind of difficult because first, the wall crossing phenomena will happen. Second, we need some explicit example to do the calculation. But the setting is like this. You take some elliptic K3, which admit holomorphic section. Then use hyperkahler rotation, you make this to be bi-Lagrangian section, in fact. Then based on the Deuce-Matic result, as long as you have global Lagrangian section, you can make the total space into cotangent bundle of total space quotient the lattice. Then at least you can get the canonical metric, Ricci flat metric on the total space without all the singular fibers. Then finally, we hope somehow we can get some explicit metric on the total space. But that's in future. Okay. Thank you.
Any questions for Jie?
What was the reasoning behind BPS? I mean, you have this statement that you took omega to be plus or minus 1. So
Oh, okay. So you mean let's see, this one?
yeah.
Oh, that's the standard result on K3 surface. When you think about holomorphic disks, when you think of holomorphic disk here of mass of index 0, then it turns out just when in one direction you will have the holomorphic disk. That's the alpha line. And so if you take the positive orientation, that's a unique family of holomorphic disk. And if you take the reverse orientation, that's another holomorphic disk. So that's the reason you only have positive 1, negative 1 here.
Let's thank Jie again.
Thank you.